Hey, so I am doing the exact opposite of my usual things today. Instead of a well-crafted, well-shot video, doing a live stream. Instead of doing analog audio. Can't retake. No, I can't because I'm live. Instead of doing analog video, we're going to do some digital audio. Doing the exact opposite because I'm helping a friend out with a project that he's working on. And given that I don't know much about digital audio, I thought I'd make myself a little PCB with the basics on there. So the PCBs and DigiKey both arrived today, which is very unusual. So let's talk about what we're building while we're building it. So what I'm trying to build today is, look, you can see the top down. There you go. What I'm trying to build today is a circuit that takes stereo audio in and outputs stereo audio. This would be a very simple circuit in the analog domain. It would just involve at most, or at least, 3 pieces of wire and some connectors. But to do it in the digital domain, we have to do some analog to digital conversion, some digital to analog conversion, and all that sort of stuff. I'm trying to open this bag up off camera so I don't show my address and stuff. So I built up this schematic. I should set up a way to share the schematic, but it's pretty simple. Let me open up the board and I can just walk you through it. X-Acto knife. I built up this board as a quick little test where it has audio input, analog to digital converter, a clock for clocking it. It spits out a format called I2S, which is unrelated to I2C, which I'm at least more familiar with, but I2S is basically a stereo digital format, not designed for transmission over length, but really for inter-chip audio communication. Outputs that, sticks it into a digital to analog converter, and should spit it out on the other end. This is my board. Didn't do the greatest of layouts. Let's zoom in so you can see how not great the layout is. That is unrelated. Please don't look at that. Come on, camera. All right, so here is our board. Nice 4-layer board, standard, gold-plated. Audio signals come in here. They go through a capacitor for DC offset removal or just decoupling. Goes into, what are these resistors for? I believe there are op amps in here. Yes, there are op amps in here. So this one is the feedback op amp. This is the input op amp. This sets up a gain of 0.5, inverting gain of 0.5. So there's 2 channels of that. Goes into the analog digital converter, a bunch of decoupling caps. The schematic or the data sheet wanted way more decoupling caps than I think is necessary for a circuit like this. And this is our, let's find it. That's our DAC. These are some jumpers. I'm running low on jumpers. This is a crystal oscillator. We'll need that in a second. Ferrite beads, audio jacks, and of course, it's the last one I pull. Analog to digital converter. So this is our analog to digital converter here. It is a Cirrus Logic Wolfson Audio WM8782, which is stereo audio, able to spit out 24-bit, 192 kilohertz max. The way you configure the format is with these 3 jumpers here. They're tri-state inputs, so this is not connected. The format is not connected. I believe I'd have to look up the data sheet. That means 24. No, the next one is sample rate. Yeah, so format is what's the binary output format. There are 3 options, I believe: I2S, right justified and left justified for bits. FSAMP-N is this one here. That is the sampling rate. Then IWL is word length. So there's options between 16 and 24. Is there 32? I don't know if there's 32. I don't think there's 32. Anyway, this lets us set those. Then it spits out I2S. Now, there are 4 digital channels involved in I2S. There's BCLK or bit clock. That goes high for every pulse, for every bit. The LR clock. So the audio is in 2 words. The first word is the left channel. The second word is the right channel. They flip back and forth. This LR clock just goes high, low. Every, let's say we're 24 bits, every 24 BCLKs, this goes low and this switches to high. D out is then the data. So for every bit, this is either high or low, depending on what that bit value is. Then MCLK is master clock. We have a 24.576, I believe, megahertz. Yeah, 24.576 oscillator. That generates the master clock that is far higher than the sample rate. But this has to do, I think it's a delta sigma converter or successive approximation, then delta sigma over here on the digital to analog side. It needs a clock rate that's much faster. This is clocked at 128 times 192 kilohertz, which is how I get this 24 megahertz here. And anyway, those 4 lines go out to jumpers, so I can tap out and look at them, or I can just jumper them over to be the inputs for the digital to analog converter. It doesn't have any configuration. You can work that all out from what it's getting over here. And it spits out 2 audio signals, probably via these 2 capacitors here for more decoupling. I already know there are some errata, some errors in this design, because what happens is whenever you click submit on a PCB manufacturer, that's when you find your bugs. I think I marked them in my schematic, which might be on this computer, might be on another computer. Can't remember. One of the errors is, there's one error that matters, one that I'm going to ignore. On this analog to digital converter, there's a pin down here somewhere. These are mounted upside down on the board. There's a pin down here, pin 20, which is the master slave select, their terminology, not mine, which you either draw high or low to say whether it's in master mode or slave mode. The distinction there is that you can have one chip that is one master clock, and you can synchronize all the other chips to the same of these guys. These can be inputs, well, not D out, B clock, LR clock, and M clock can be inputs into other chips, so that you can have a bunch of these analog to digital converters all bit clock synced. I've only got 1 channel, 2 channels, 1 chip. So I've just set this one to master. Anyway,